When we talked about enantiomers, we mentioned that their physical properties are virtually identical. The only thing that differed significantly was their interaction with polarized light, where two enantiomers turned polarized light in opposite directions but by exactly the same amount. Let's see now, does the same thing apply to physical properties of diastereomers? Diastereomers arguably are more different in their structure than enantiomers. The only thing that makes enantiomers different is their mirror images of each other. Diastereomers' differences are quite more significant. And we've already seen that cis-trans diastereomers have quite different boiling points in dipole moments. For example, the cis isomer of 2-butene has a boiling point of 3.7 degrees, and a dipole moment which is larger than 0, since two dipoles add through vector addition. If you look at its trans isomer, then the two dipole moments will cancel each other out, so the dipole moment will be equal to 0, and the boiling point will be slightly lower, but still different, of 0.9 degrees centigrade. Even those that are not cis-trans, even when not cis-trans, diastereomers still have different physical properties. So if you look at these examples of dibromosuccinic acid, this is one of the possible stereoisomers, and this is another one. And if you look at them carefully, you will notice that these two are enantiomers, and hence their melting point, for example, this is a solid, will be exactly the same, 158 degrees centigrade. Okay? But if you look at the Mace isomer, which is achiral, but it's still a diastereoisomer to these two, melting point of this thing, because of its higher symmetry, is 256 degrees, so it's significantly higher. And so, a long story short, diastereomers are basically, in terms of their physical properties, completely different compounds. And since they're no longer mirror images, their properties differ quite significantly. And this also has an important point. When we get a mixture of compounds, and those compounds have very similar physical properties or identical physical properties, such as enantiomers, then it's very difficult to separate those. But if we have a method, a physical method which employs a difference in, say, boiling point, such as distillation, or melting point, such as sublimation, or solubility, such as crystallization, then we can easily separate two compounds which have different boiling points, or melting points, or solubility. And since two diastereomers typically will have relatively different melting and boiling points and solubilities, we can easily separate diastereomers. So that's an important point. Diastereomers can be easily separated. And that is an important point which we will touch upon in our next topic, which deals with the separations of enantiomers through their conversion to diastereomers.